Okay. All right, so I'm recording now. So there's one thing I think I should have mentioned last time that I didn't, which is relating. There's actually a rule before the product and quotient rule that you can definitely see in the slides, but it's kind of broken apart. It's the fact that the derivative operation is linear, right? So I think that I introduced the word linear to you. I should have said that like the operation of taking a limit is linear, and the operation for a derivative is also linear. So mathematically, the fact that it's linear is written like this. So you have some kind of a constant k times a function plus or minus another function. This kind of operation being linear, what it means is that you can split it over addition and subtraction, and that you can pull constants out. So you can rewrite this as being k times the derivative of f of x plus or minus the derivative of g of x. Right, this is what linearity is. And yeah, put a little boundary there. And to simplify notation, what we can do is we can just write this without all the parentheses, and that would turn into an expression sort of like this. Okay. And okay, so now last time I briefly mentioned product rule and quotient rule to you, and I wrote these formulas. So hopefully you took a bit of time and you got comfortable with these formulas, right? So product rule, what it's about is if you are trying to take the derivative of a product of two functions, f and g, then what you compute is actually going to be the derivative of f times g plus the f times the derivative of g. Okay. And this is not, so this isn't what you would kind of hope the product rule to be, but this is the correct version of product rule. And then quotient rule, now you have a quotient of two different functions, and you have this kind of thing happen. So notice the difference, the two are kind of related, right? So if you write f prime g minus f g prime, if you use the same order as in product rule, then all you have to do is you change the plus into a minus, if you can memorize the order in this way. And then, of course, you have to remember to divide by g squared. But I'll note that the thing I tend to do when I'm computing is I actually use gf prime minus fg prime over g squared. So what I tend to do is I tend to swap the g and the f prime in the beginning. And the reason, there's sort of a reason for that. The reason is that the derivative is something that actually can expand quite a bit. So eventually you learn about chain rule, and then it's kind of easier to think of it as being like you're taking a derivative and you just keep taking derivatives until the process terminates. And so in that way, like taking a derivative kind of expands out, and it's just nicer to put that as like the last step. So I tend to do quotient rule in this order. And I told the other class this somewhat, so maybe I should also mention it here. I have a very silly mnemonic. Um, like that. What's funny is that I only discovered this mnemonic after my undergrad. Like it was probably the month after I finished all of undergrad that I then realized, oh, if I use U for up, D for down, same notation that I use for Rubik's Cube stuff, then you can just write the numerator as dude, spelled terribly, and the derivatives are in the back, which is actually what I prefer. And then just over D squared. Yeah. So yeah, there's that. Or you can memorize it the standard way, I guess, or you come up with your own way. Like the thing about mnemonics is you use the thing that works for you, right? Okay, so with all that, let's go ahead and finish the rest of the problem set. So 6a is just using product rule. So we take the derivative of this, that's going to be 2t plus 1 times, and then we just copy down the other guy. So that'll be 12t squared plus 1. Or, oh, no, I was taking the derivative. No, that was, what was I doing? I copied the other guy down. Exactly. Oh no. Computer's being weird. Something's. One node is not responding. I might need to kill something. Okay, is it back? It's back. Okay. Yeah, now it's working. Good. Plus t plus 8, and then plus. So this was first half of product rule. The second half, I copy the first guy, take the derivative of the second guy. T squared plus t plus 1 times the derivative of the second, which is going to be 12t squared plus 1. Okay, so that's 6a. Any questions? All right, so part B, you should definitely just see this as quotient rule, right? So we just need to do quotient rule in the correct order. So down times up prime. So the denominator and then derivative of the numerator is 6x plus 2 minus, and now numerator times derivative of the denominator. And then all over denominator squared. Maybe I can undo that. Oh, what happened here? For x plus 14, right? Why is this computer being so slow? So x to the 4 plus 7x squared plus 3 squared. Just double check it. Yeah. Yeah. Okay. Now C is sort of a little bit different. So you could use what you already know, and what you could do is like actually multiply the x plus 4 and the x plus 5. You'd get a quadratic x squared plus 9x plus 20, and then you could do product rule using those two polynomials. That's one approach. There's another approach that involves using a generalized version of product rule, which I think is worth showing you. So I'm gonna talk about that. Okay, so there's a generalized version of product rule, and it basically works like this. So if I have, let's say we have a product of 3 different functions, right? How would we do the derivative of them? Well, one thing to try is to combine the two, sort of just choose one of the products to focus on, and the other one we just sort of keep it together as a group. And so if you group it in this way, then you apply product rule once, what you will get is, so first is the derivative of that times h, okay, plus, and then fg times h prime. That's what product rule would say. And then you'll note that what you have here is yet again another product rule. So you just do product rule one more time, and you'll get f prime g plus f g prime. And notice that both of these are supposed to be multiplied by h. So we can put a set of parentheses there, and then f g h prime. Okay, and then finally, distributing this h, we get f prime g h plus f g prime h plus f g h prime. And now notice that there's sort of a pattern. If we just look go from here to here, notice what happens. Right? Each of these terms, we have a derivative being applied to one of the functions, and the other two functions we just leave as is. And so this is really like how you would generalize this to an arbitrary amount. So if you had like 10 different functions you're multiplying together, there's a very, and then you're trying to take the derivative of that product of like 10 different functions, is you can generalize this product rule to make it pretty easy for yourself. It's not too hard. So, but here we just got this, and we can just apply this generalized product rule to it. Yeah. So, well, it says take the derivative of this x plus 4 first. That was just going to be 1. So actually for this, what I'll do is I will actually just explicitly write the 1. And the reason for that would be just to show my grader, like what it is that I'm doing. Obviously, like, you wouldn't normally write the 1, but here, the reason to write the 1 is kind of just to like show your work, show your thinking process. And then the next term, we've got x plus 4 times 1 times x squared plus 6. And then lastly, we have x plus 4 times x plus 5. And then the derivative of the x squared plus 6. So you should remember that derivative of x squared is 2x. Or maybe not remember, but like you should be able to do that because it's just power rule. Okay. And so, yeah, that's your answer. And if you really wanted to, you could rewrite without the ones, but I'm just going to leave it like that. Okay. Any questions? No? Okay. Let's keep going. So 7, A and B are all about using this table. And again, it's just product rule and quotient rule. So the only thing here is now it's asking for A prime evaluated at 2. So the way that you would kind of think about this is you want to take the derivative first, and that'll create some function for you. And then you want to evaluate that function at 2. Okay, but we can kind of combine both of these steps together. So I'll try to combine it for you just because like there's not that much space, I guess. So taking the derivative, we would expand this out, right? This is just product rule. So we have f prime, and then normally we would write x, but because we're going to evaluate at 2, we are going to put it 2 in. Okay, we plug in 2. And then g also is going to need to be evaluated at 2. And then plus, and then f of 2, g prime of 2, right? So I did a product rule, I evaluated at 2. And now we just go ahead and read data off of our table. So that's the row with 2 in it. And we have 2 times 7 plus 5 times 6, which is going to be 14 plus 30. That should look like a 0, which is equal to 44. Okay, and B works very similarly. So here we have quotient rule. So we denominator to numerator, we sort of go upwards, then we go downwards, if you think about it that way. So, and we plug in at 1. So g of 1, f prime of 1 minus f of 1, g prime of 1, all over g squared, or g of 1 squared. And we read data off of our table. So that's the first row, we have 4 times 1 minus 3 times 2 over 4 squared. Okay, so that's 4 minus 6 over 16, which is going to be negative 2 over 16, which is negative 1 over 8. Okay, that's a 2. Okay, good so far? Questions?
You might have already said this, but on B, how did you know to do that formula?
How did I know to use quotient rule?
Yeah.
Well, because this is a quotient of 2 functions. You're dividing one function by another.
Okay, I got it. I see now. Thanks.
Yeah. These are really appropriate names for things. Product rule, quotient rule. It's a product of functions. It's a quotient of functions. Um, I mean, technically, one thing is you actually never need to use quotient rule, but sometimes it's just easier to use it. Like, um, I remember like in high school learning like you just at the high school level, I never needed to use quotient rule. I could get away without memorizing it. But the way to do that is you have to rewrite it as like a g to a negative first power, and then you're kind of using a chain rule. So you can replace quotient rule by using product rule plus chain rule. I don't know if that's what you're getting at, but there is a way to avoid quotient rule. But you can just also just learn to use quotient rule. Yeah. Anyway, um, all right, let's go ahead and look at 8. So 8, there's something tricky about 8, which is in the parts C and D, but A and B are pretty straightforward. Okay. So when you're talking about average, you normally are just taking like a sum and then divided by the number of things. And that works out here just fine. Average cost is just going to be the total cost divided by the number of items that are produced. So there's your formula for A of X. A prime is all it's really asking you to do is to find a derivative of this. Okay? Like all this stuff, that's just saying like it'll be in terms of these things, right? But this is just a product or quotient rule. This is just a quotient rule. So we have x times c prime of x minus, and then c of x times, I can put a 1. Derivative of x is just 1. Okay. All over x squared. Okay. That's better. All right. So now c, when is this derivative? When is this positive? So notice that the denominator is x squared. That is always positive. So actually, this boils down to the numerator. And how did I phrase it? Maybe I can try to do it like that. So a prime of x is positive when, and so as I said, it boils down to the numerator being positive. And what we can do is we can sort of say, we can rearrange it. So x c prime of x is greater than c of x, right? Is that clear? Say yes or no.
Yes.
Okay, good. All right. And then what we can do is actually divide this x over. And notice that if we divide x over, we actually get a of x. So we end up with c prime of x is greater than a of x. Okay. And now this is actually crucial. So we can actually reason about this and realize our answer for D. But I'm going to also write the other half of C right now. So when is it negative? That's less than 0. And we can do exactly the same thing. And then we divide x over. And we notice that that is a of x. So we get this. Okay, so how do we reason about these things? Well, if we sort of say this in words, this is the rate of change of cost, and this is average cost, right? And this is the change in average cost. So how did I say this? Yeah. Why does it make sense? So I said if the change in cost is greater than the average cost, you expect it to pull up the average cost. Right. So that's sort of the intuition that you kind of have to maybe think about it a little bit. It feels like it makes sense. Hopefully. All right, and then you can also just repeat the same thing with the other direction. If the change in cost is less than average cost, then you expect it to pull the average cost down. Just to phrase it in parallel, I should read it down. Okay. So hopefully that feels good to you. The rest of the problems are pretty straightforward, actually. They're just derivatives again. With 9, the answer is very messy, right? Because in this, we have to do both a quotient rule and a product rule. And I think it's more illustrative to show you how that would work in the abstract. So instead of having these explicit functions, if we instead consider f times g divided by h, and we're trying to take the derivative of that, okay? So the way that you should parse this is the quotient is the outermost operation that is being performed here in this function. And so when you're taking the derivative, you want to take the derivative of the outer guy first and then go inwards. So we do the quotient rule first, and then in doing that, we're going to wind up having a product rule happening inside. Okay, so quotient rule first. All right, quotient rule says h times the derivative of the numerator minus numerator times the derivative of the denominator. Okay, and then all over the denominator squared. So now you can see this is where the product rule is going to show up. So then we have h times f prime g plus f g prime minus f g h prime. I should make that parenthesis a little bit bigger. And then it's all over h squared. Okay. And then, if you really wanted to, you could probably distribute that, but I'm going to leave that as such. So this is what's going to happen here, except with explicit functions. And it's going to be, it's going to look a little bit weird because we have the numerator is going to probably show up in 2 lines. There's not that much space. Okay, so yeah, now we just go ahead and do it. So denominator times derivative of the numerator. I'm going to put square brackets to do that. And then I'm going to now take the derivative of the numerator. So that's going to be product rule. So now in the mindset of doing product rule. So product rule is going to say I take the derivative of this guy. And at this point, I should also say something about the derivative of the square root. So you're used to doing that, and you're used to taking its derivative and it being 1/2 x to negative 1/2. And this is actually the same thing as this if you rewrite it. And when you take derivatives long enough, you get used to this pattern that the derivative of square root of x is just 1/2 square root x. So I'm going to just straight do that or write that down instead of the negative fractional power there. Okay. It's just a pattern that you kind of get used to after taking derivatives for a long time. Okay, so that is part of almost the first half of product rule. We also need to copy down the other function. Okay, so there we've got the first half of product rule. Now for the second half, we copy down the first guy and take the derivative of the second guy. And so that's 5x to the 4 minus 7. And we can close off this this square bracket. Now this in total is actually the first half of quotient rule, right? We then have the second half of quotient rule, which says subtract off numerator times derivative of the denominator. So numerator, I can just copy that. And now times the derivative of the denominator. So 3, and then it's power rule for this guy, minus 2x to the negative third, right? And then lastly, this is all over denominator squared. And so that is our answer. Okay, any questions on that? No? Okay. So now number 10, this one is really quite easy, actually. The only thing to note is you need to understand what this symbol means. So this means you're taking two derivatives. You're taking the derivative of the derivative of this function. And so one way we could unpack this is we think of it as like we have ddx of the function. And then we can just write ddx, and then what's the derivative of this guy? Well, it's going to be 15x squared minus 37. Okay, so we have done one of the derivatives, and we have one more to take. So we just take another derivative, and we end up with 30x. Great. So much easier than the previous problem. And then the last guy, s double prime. So this is just another notation for the second derivative. And here's our function. We have to do that, and then we have to plug in. So one way to phrase this is this problem is really just asking you to find s double prime of 8. Evaluate the second derivative at 8. Okay, well, first we need to go ahead and take two derivatives. So first derivative, this is just going to involve power rule, or not power rule. Yeah, so 4/3 t to the 1/3. All we do is just subtract 1, right? Minus 7. And now second derivative is, so now we had to do power rule to this. Bringing that down, we get 4/9, and then t. And now we need to subtract 1 from this. So this is the one part where like people might make a mistake on. So you have to know how to subtract 1, which will actually give you negative 2/3. And the 7 disappears. Okay. And lastly, we can now plug this in at 8. And so the way I would think about this is firstly, we should interpret this guy. So this power is, you can think of it as being a cube root first, right? The 3 in the denominator, right? The 1/3 power is a cube root. So you can do the cube root first and then raise it to the power of -2. Okay, so we can do cube root of 8, which is pretty easy. It's just 2. So we get that, and then raise it to -2nd power. Right. And so what is 2 to the -2nd power? Well, we would square it and then put it in the denominator. So we get 1/4, and then just multiply. So we get 1/9, and we have to put units because this problem has units. And in particular, this will be feet per second squared, since this is an acceleration. Okay. And so that's all for the problem set. Are there any questions? No? If not, then I will stop recording.